So welcome back again. As I discussed in the last video, polar and non-polar molecules. So we shall today see how these molecules behave in the presence of an external electric field. So this is polar. Okay, imagine I have a piece of a dielectric which is polar. Now you know that every polar molecule has its own dipole moment. So we must write dipole moment is not equal to 0. This is for a single molecule, not for the whole slab. Remember this. So don't get confused. P will be non-zero for every single molecule, whatever it is made of. So you know the direction of the dipole moment is given by from minus to plus charge. So imagine this is a molecule, a polar molecule. In general senses, all these polar molecules are oriented in such a way that the resultant dipole moment in this piece of the dielectric is 0. That is, this is one molecule, this is another molecule, this is, so in somehow all these molecules are randomly oriented. This is plus, this is minus, this is minus, this is plus, and so on. So what a feel you must be getting is that the dipole moment of these atoms are given by this negative to plus, positive, negative to positive, negative to positive, and so forth. So if I have a billions of number of atoms, obviously every slab contains a billions of number of atoms, molecules, sorry. So each and every molecule are oriented in such a way. Remember, we have no external electric field. I must specify this. We have no external electric field, that is E outer or external field is 0. So in this sense, this piece has, okay, come here, this piece has, suppose this is one dipole moment, this is another dipole moment, this is another dipole moment, this is one more, so it is being cancelled by this. So remember one thing, the dipole moment of each and every molecule will be cancelled by the next molecule there, so that the net dipole moment of this slab or piece is completely 0. Okay, so its dipole moment will be cancelled by this, its dipole moment will be cancelled by this one, and so forth. So obviously the dipole moment of the total slab is 0. Electric field is 0 and their net dipole moment is equal to 0. What if I apply an external electric field? So in that case, when electric field is applied, that is E outer is not equal to 0. So these all dipole moments, that is molecules, because I am indicating these arrows for what? The molecules. So each and every arrow align themselves in the direction of the electric field, so that the device, the slab has got a net dipole moment. Remember, that is the direction of the electric field. And what happens if the external electric field is applied? Because electric field is this direction, or for this it is this direction. So obviously this part of the region will be positive. So we have a positive background here. Obviously the negative background must be of that side. So all the negative ions try to accumulate themselves toward the positive region, so that now the dipole moment of this molecule becomes what? Minus and plus, and they even reorient themselves as well, minus plus. So now focus, the dipole moment direction is from negative to positive. So this is the dipole moment of first molecule. Say this is P1, this is P2, this is P3. All the dipole moments or even arrows are now orienting themselves towards what? The external electric field. This is my external electric field. So what is the outcome of this situation? I have put what? A dielectric of kind polar. External electric field was 0. The net dipole moment of the piece was 0. Now again 0. This is replaced by this. Now this, when I switch on an external electric field, what happens? The system or the slab acquires its net dipole moment. Okay, so this is how we have simply called polarized the dielectric. Okay, in such a situation, this piece has produced. Now see one more figure. It will be quite clear, or it will be clearing all the mist for what we are. So this is, I am simply putting this here, minus plus minus plus minus plus. Okay, just a minute. So what is it producing? See, this is your external electric field, right? Now see, this left side of this slab has acquired some negative charge, right? And the right side of the slab has acquired some positive charge. All right side atoms will acquire some positive charge, but this charge is being cancelled by its effect, this is being cancelled by this effect, and so on. So finally what is left? We have a region of negative and positive layers, but the electric field is here in this way. As I told earlier, this will be the background of positive charges. So we get an arrangement of negative charges this way, and this is of positive charges. So what happened? Okay, now this is a kind of layer. This is a kind of layer of positive and negative charges. So they are playing the role like what? Plates. So charged plates. So they will obviously produce what? Their electric field, directing from plus to minus, and this is called EI, I for induced, or field of polarization. This is external electric field this way, and the induced field is now opposite to the applied field. So the net electric field will be where? So the net electric field is given by E vector. I am writing the vector equation. Remember, this is external electric field plus the polarized electric field. What about the magnitude? Remember, this is vector equation. So what about the magnitude? In magnitude, what we get? The net electric field is the E outer minus E induced. That is the net electric field. In later section, we shall discuss about the dielectric constant. Okay, for the sake of now, this is the relation between the external and the resultant electric field. So you must be getting that inside the dielectric, the net electric field will be again in the direction of the applied field, but somehow smaller than the external electric field. It means the field inside the dielectric or polar type is now reduced than that existing in the outside. So if we place a dielectric between a positive and negative plate, wherever the dielectric exists, the electric field, what happens? It reduces because of the polarization. Okay, so far we have discussed what? Polar dielectrics. Same will be non-polar dielectrics. So let's discuss that. So here we shall talk about the non-polar molecules. What are non-polars? Which have their center of negative charges and positive charges lying at the same place, so resulting no net dipole moment of their own molecules. Okay, so imagine this is a single piece this is plus and minus. This is one single molecule. Again, this is one molecule. These are molecules whose positive and negative charges are lying at the same point, or you can say coincide. And this is the situation where external electric field is 0. What happens if I apply an external electric field? So in that situation, obviously its dipole moment is 0, it's obviously 0. So net dipole moment of the whole piece is equals to 0. Now what if I place it in the presence of an external electric field? It is not equal to 0. Now remember, this is the direction of the electric field, external. So obviously this part consists of a positive layer, a positive region which is producing the field, and that is of negative region. So this molecule gets distorted. Distorted means, say this is your single molecule whose positive and negative charge lying at the same point. Now what happens? The electric field distort, or it will try to pull the molecule away from its own situation and resulting a new shape like this. It becomes paraboloid, and this is the next structure. So all these molecules in this piece will become like this. Okay, very simple. Now again the scene is little more same as in case of polar molecules. The electric field has distorted the molecules, it reshaped it. Now is there any kind of dipole moment producing in each and every molecule? Obviously the answer is yes. See, this is its dipole moment from negative to positive. It is negative to positive, negative to positive. So where we have got what? Each and every molecule has got its own dipole moment. So the next picture is very clear. In the presence of external electric field, all the dipole moments are now formed and they are aligned in the direction of the applied electric field. Okay, so we have got again the same equation in the, that is external electric field will be equal to the field inside then field net electric field, or net electric field equal to E outer plus E induced. And how this E induced is produced, you must be getting again, if I remove all these positive charges, all these charges, what I get? A layer of negative charges, a layer of positive charges, and they will produce their own electric field. This is induced electric field, and this happened because of the presence of external electric field. So inside the material, what happened? All the molecules become first single dipole, and then by the effect of the field, these dipoles get oriented in the direction of the field and finally produce a net electric field inside the piece, and which is less than the external electric field. So in magnitude, the net electric field is equal to what? E outer minus E induced. So that is, the net electric field will be less than the field applied externally. That's it. So this is how the non-polar molecules behave in the presence of an external electric field. Okay, hope you might have got a little bit of the concept. That will make my tryst hopeful, and again doing best for you guys. So for today it's bye bye, take care, and do note all the things.